elastic deformation. So elastic deformation, in that sense, well, we are talking about deflection is equal to PL over AE. Over AE, not AB. Which we have learned the root equation last week. Okay, so that's what we're going to do for the next 1 hour. Okay, we're going to look at how this can be developed, and then we're going to look into a problem set. Okay, anyone so far, any other question? Equation substitution? No, you cannot just do equation substitution. Okay, so I don't see any question. I don't see anyone raise their hand. Okay, so I will teach. I will show you. Yes, anyone?
Yes, can you hear me?
Yes.
I'm just trying to wrap my head around this. So, dy and ay support the same weight. I kind of expected dy to support a little more because forces are pointing that way. I'm just trying to wrap my head around it.
Now, dy and ay only can support forces in the vertical direction. So the 500 and the 200 is not affecting the load on ay and dy. Jordan, does that make sense now?
Yep, thank you.
Okay. Whereas ax and dx, their values will be affected by the 500 and by the 200. Okay. Yep, I like what Jordan has done. Okay. Clarify things like that is really good. Okay. I have Jiang every week except test week and reading week. Thank you. Right. So I'm going to write out the solution procedure, okay, to analyze or to analyze statically indeterminate structures. Okay, so solution procedure. To analyze statically indeterminate structures. So I'm going to write out some definition and terms. Okay, then I'll show you through an example. So the redundant reaction a key thing to emphasize down here is wrong. A key thing to emphasize down here is the word redundant. Okay, the redundant reaction are placed with unknown loads which along with other applied loads must have compatible. It's a lot of words, okay, but don't worry about it. Okay, compatible deformation. Okay, so just to write out in the form of math, so deflection of the applied load plus by the deflection of the redundant load, not resultant, must be equal to 0. Okay, the term compatibility means deflection due to the load and deflection due to the redundant must be the same. So when you put both equations together, it must be equal to 0. Okay, so let me define what is delta L, which I've just spoken. So delta L is the deflection due to the actual or applied load. Okay, and then delta R is the deflection due to the redundant load. The definition of redundant means it is not necessary to be there. Okay, even though without it, you'll be fine. The structure can support itself. Okay, so I would like to emphasize on this is that note. Okay, this is important. Okay, I want to emphasize this. Okay, this is a key point. Note that delta L, the deflection due to the load, and deflection due to the redundant load are always opposite in direction. Okay, and rather than load, I'll emphasize in summation of the applied load. Okay. So what do I mean by that? So we're going to have two cases. Okay, case number one and case number two. Okay, case number one and case number two. If the summation of the applied load, okay, if the summation of the applied load is positive, let me draw a table form. Okay, if the summation of the applied load is positive, positive in this sense is in what? Tensile. Okay, the redundant load will be in what? Compression. Likewise, is the summation of the applied load is inducing a compression. Okay, the redundant load must be inducing a tension. Okay, it's always the case. Okay, you will never have a case where the applied load and the redundant load are in the what? Same direction. Okay, you will not be, you don't have that. Okay, right. So now we are going to look into an example, not a teaching example. Okay, when I say teaching example is one that you can get out from the textbook. Okay, so we are going to look at the structure. Okay, analysis of statically indeterminate structure. Okay, so I'm going to use the next page. I'll leave this on for you to copy for 30 seconds. Okay, if some of you are copying, you can do so. Anyone, any questions while waiting? No? Okay. So I'm going to take this. And then we are going to So now all these images are available on Avenue to Learn. When I started class, I told you all to download. So if you can go on Avenue to Learn to download all these images, please. Thank you. Okay, so we're going to look at this structure now. Okay, so as you can see, this structure is very similar to what I've drawn earlier, except now is in the vertical position deliberately. Okay, so we can today also apply our hangman theory. Yes, we can apply our hangman theory to this example today. Okay, so what we are going to do now, okay, we see a structure like this, and we realize that the structure is statically indeterminate. Okay, so as I said, we're still in the procedure. Okay, so now we are going to remove the support Okay, we're going to remove the support at point B. Okay, we're going to remove support at point B. Okay, so point B, we're going to remove the support. So when we remove the support at point B, what's going to happen? So I'm going to sketch. This is what's going to happen. Okay, so we are going to sketch. So this is okay. And this is exaggerated, by the way. Okay, I deliberately want to exaggerate this. Okay, so this is our point A. Somewhere down here is our point D, our point C, our point K, and our point B is over here. Yeah, I'll put B over the other side. Right. So when we remove the support at point B, the structure is able to extend, right? Because there's nothing resisting it. So if I were to draw a green line, if we were to draw a green line here, okay. So there is a extension or yeah, there's an extension because it's tensile loading as you can see. So what we have down here, okay, this over here, right? So let me put in the loads also. Okay, the extension is due to the loads. So the loads of 300 kilonewton and the load of 600 kilonewton. Okay. So when that's the case, you will have an extension, okay, from the original position, and this extension over here that we have to calculate is our delta L. Okay, so we remove the support at A, right, and we let the structure extend. Okay, I did not. I have to draw the support over here. And then the next step, okay, the next step after we have done this, right, we are going to add. Okay, before I go on, when we remove the support at point B, what we want to determine is delta L. Okay, we're going to determine delta L. Okay, we're going to determine the extension. Then the next step is we are then going to add a redundant load or de-redundant load. Okay, we're going to add the redundant load at point B, okay, such that the total deflection Okay, the total deflection is